So maybe I'll use this opportunity, if there are no questions, to ask Vlad the questions I tried to ask. Vlad, what was the lowest conductance values that you get in your models?
Yeah, I saw your question. Thanks for your question. So so if we compare to the current Earth, then and that's, of course, that depends on the XUV flux, right? So when we have the XUV flux at around 10 times of the current, then the calculations suggest that at least at heights about between 100 and 200, that's where the most of the energy deposition occurs, right? In the thermosphere, the permanence and conductances are very comparable. So that's very interesting. So when I said the factor of 5, that refers to the conductances for a case of 60 times XUV fluxes, but the 10 times are pretty much, within the 30 to 50% are comparable to the profile that we obtained for the Earth-like conditions.
Thank you.
So I've been frantically searching for the raise hand feature, but just realized that I'm a host, so don't actually have the raise hand. Can I ask a question?
Yeah, go ahead.
I'll go ahead. Thanks. So it seemed like from both Tetsuya and Tom Craven's talks that one undercurrent of the talk was the importance of the atmospheric composition and the chemistry happening in the atmosphere for determining the composition in the upper atmosphere. And I wondered if I, A, took that undercurrent away correctly from those talks, and B, whether this applies to all of the other processes that we heard about, the ion escape that Moa talked about, the hydrodynamic escape that Carolina talked about, yeah, all of these other processes as well.
Dave, this is Tom. If I could jump in there, yeah, composition, at least photochemical escape, matters a lot. The real question is in the early solar system, like Mars, Venus, what is the composition? And I imagine there are people who know that, but I have to admit I've not followed that out because it involves a lot of things. As you move from the proto-atmosphere to later atmospheres, it'll certainly affect for the smaller planets photochemical escape.
And for Moa, if the upper atmospheric composition of Venus were different, would you expect the same amount of shielding?
I agree with Cravens. If the composition of the atmosphere were different, then of course it would change how it looks like. The scale height of the upper atmosphere would change. Maybe the ionosphere would change, and so the induced magnetosphere would change probably, and that would change the escape rates. Is my thinking. Isn't that just to continue that discussion? So there's like a big difference between Venus, Mars, and Earth in this sense about the composition. So we have nitrogen mostly on Earth, which creates a higher scale height, a higher exabase. While for Venus and Mars, the exabase is much lower altitudes. That changes what needs to be sort of protected, right?
We
yeah,
have,
so-
oh, sorry, go ahead. Karen.
No, it's fine, it's fine. I will raise
Oh,
my
no,
hand.
we just have two people who have raised their
Yeah.
hands, Vladimir and William Peters. I can't see the names.
Will, why don't you go ahead?
Hello?
There, I got myself unmuted. I was struck by Fran's talk about the zoo of magnetospheres. And the topic of this is, do magnetic fields affect the escape rate or the atmospheric retention time? But Fran showed that Saturn and Jupiter have mass loading, which may or may not affect the atmospheric retention. So should we expand what we're thinking about and think of planets in addition to composition? Do we have to think about mass loading in the magnetosphere or plasmaspheres or something like that? Is that another dimension that has been shoved under the table that we really should consider? Dead silence.
Anyone from the panel wants to reply?
Well, Bill, this is Tom again. You're then getting into the issue of planetary satellites and how much atmosphere is escaping from the planetary satellites, which thus affects the magnetosphere. So it is a whole other dimension.
Is it important?
Well, it's obviously important for Saturn and Jupiter. The terrestrial planets, I guess not so.
We have two more hands which are up. I'd go chronologically with them. First Vladimir and then Carolina.
Yes, I have. It's a comment and a question to ask people about the photochemical escape. So the point is that now we have the photochemical escape, which is most important for Mars, right? Because of the energy of hot oxygens around 1.99 electron volts and escape velocity, right? So, however, and nitrogen is like 1.77 electron volts, and which is not that important. But if we relate it to the conditions of closed exoplanets irradiated with such a huge fluxes that I briefly discussed today, then and the heat deposition is high, then we can expect the inflation of the exobase all the way to a couple of 2 or 3 Earth planetary radii that will reduce the surface gravity. So, and therefore, reduce the escape velocity and allow the nitrogen and oxygen probably escape. That's I never looked at it, so I was wondering, what's your opinion on those possible effects of the hot oxygen and nitrogen escape due to inflated exobases, exospheres?
I think that's an interesting possibility. Of course, in those situations, wouldn't the hydrodynamic escape dominate in any case?
Yeah, right. But I'm talking about, you have the on top of it ion escape and but yeah, of course it will probably, but in some case might be not. And again, the hydrodynamic escape is pretty it's pretty sensitive to the chemical composition. So therefore, for some chemistry that can create efficient coolants, that might prevent the hydrodynamic escape from 60, as I discussed, to might be to 100. So that's the question that needs careful consideration. But the photochemical escape, probably one process that may contribute. That's, as was hearing your talks, I just started to think that might be a one way to lose oxygen and neutral oxygen and nitrogen from the planet before hydrodynamic escape starts.
Well, I guess someone should explore that, you know?
Okay.
We have a comment from Mike Limon, but before going to that, I'd like to ask Carolina, who has her hand up for quite a while.
Thanks. Yes, I was going to answer to Dave, and in relation to what Vladimir just said, the hydrodynamic escape is, I think, is a process well related to the luminosity, so the high energy radiation from the star, and the lighter elements will be the ones that leave first, and then they might drag the heavy elements in the way. And we have seen escape from heavy elements in HD 209. And we are also starting to see escape from the helium line in some exoplanets. But I do think that the escape would be related to the amount of, like, the available material in the atmosphere of the exoplanet that is that can escape. But I will suspect that the more rich chemistry will happen very low in the atmosphere. So the hydrodynamic escape will need to be very strong in order to leave these heavy elements. I hope that was Dave was asking.
Yes, thanks. Thanks.
So we have thank you so much, Carolina. We have a comment from Mike Limon in the chat section, and his question is to rephrase Bill's question. Is this escape from moons important for the escape from the planet itself? More specifically, does precipitation at Io's or Ganymede's magnetic foot point lead to a significant planetary ion outflow? And how much does a mass-loaded magnetosphere change auroral zone outflow? And I'm seeing some answers to that in the chat itself. If anybody is interested in discussing that point, please feel free to do that. We have another hand up from Dibyendu.
Hi, so this is a question for Carolina. So I was just wondering, would you see detectable Lyman alpha signals from star-planet interactions for an Earth-like exoplanet with the magnetosphere like that of Earth interacting with a solar-like wind, or would that be too weak? That's the first question that I had. And the second question was, can we use the flux of Lyman alpha emission that you're getting from star-planet interactions to get a handle on exoplanetary magnetic fields?
Yes, yeah, thank you, Divenyu. I saw your question in Slack. I didn't have time to answer. So in relation to the first one, I think that for an Earth-like atmosphere, the amount of neutral material that you will get in order to see a strong signal will be not that high. So I don't know. In my opinion, I don't think that you will have such a strong absorption as you see for the hot Jupiter type of planets or for warm Neptunes. But in the second part of the question, I think, in my opinion, we could use the line symmetry, but we need to, in order to make a very constrained, we need to reduce the amount of free parameters that we have in the models in order to get a good estimate. But I do believe that you could study the magnetic field with the transit signatures in the lines.
Okay, thanks, Carolina.
You're welcome.
I see a few more hands going up. I'll go with Ofer first and then with Eric.
I just want to quickly add to what Carolina said. I think if you want to try to get an information about the planetary field, you have to also have a very detailed knowledge about the stellar field at the same time, if you're looking at star-planet interactions. So you need to have a lot of constraints on the system to find the one parameter that is less constrained.
Mm-hmm. Mm.
And we have Eric.
Yes, I was going to just follow up on that about the stellar magnetic field. So to Caroline, is it the case that the width of the lines is comparable to the rotation speed of the orbital speed? Because if for example, the the planet is within the Alfvén radius of the stellar field, the orbital ejection of material could be sent along field lines, which could then be pushed out radially at a speed comparable to the orbital speed. So I wondered if it's true that you see the width of the lines being comparable to the orbital speed.
So in the case of HD 209, I think I don't remember, the orbital speed is around 100 and something kilometers per second, and you do see absorption to these velocities, but I will say that it's a combination, right? Because it's the material that left the planet and is in a cometary tail trail in the planet. So it will have a velocity that is
So
combination between the orbital velocity and also the scale, like the wind velocity, and the velocity that it will have with the interaction with the stellar wind, right? Because there is an interaction region there, and all along the cometary tail that sees the star. So yes, I would say that there is velocities.
maybe some combination.
Yes, there is a combination. Yes, yes. Especially for these exoplanets, like if they are very close to the star, they orbit very fast, so they have periods of days, and so yeah, orbital velocities are very high.
Oh, we are over 5 minutes from our stipulated deadline of a time. So I would like to take this opportunity to thank all our speakers in this session and all the audience members to patiently listen to them and ask them questions and discuss their research. I would like to close this session and go into break then, and hope the next session is at in half an hour, actually, starting at 9:30. So we'll see you there. Thank you so much.
David, is there anything you want to say?
No, thanks everybody for staying so close to time. I think I'm the one who went the furthest over my time. So we'll see you back in 24 minutes, and I'll put up some slides that just rotate through for the next 24 minutes.